In this video, we're going to use some of our previous examples and just do a couple different kinds of problems using the point, line, and plane that I have written here. So the first thing that we're going to find is a line that is through point A, and perpendicular to plane P. Okay, so when you think about writing equations of a line, you should think about what do I need to know to write parametric equations of a line in R3. So one thing that you need to know is a point on the line, and we have that. That's going to be A. And then the other thing that we need to know to write the parametric equations for a line in R3 is the components of a vector along the line. So we're not given that. So I need to think about how to find that with the information that I'm given here. So what they tell me about the direction of that line, it's going to be perpendicular to plane P. So I somehow have to use that information to figure out components of a vector that will be along this line. All right, so some of this is a fluency issue, being fluent using these equations of lines and planes. And when you first work with them, maybe you're not quite so fluent, but by the time you get to the end of this chapter, you want to be more and more fluent about being able to move back and forth between these lines and planes, remembering what the numbers represent. All right, so here we're given the equation of a plane, and if you think back to how you write equations of planes, there is a formula that involves some numbers. I used n1, n2, n3 times some parentheses, x minus x naught, and so on. And the numbers out in front of the parentheses were components of a vector that is perpendicular to that plane. And so we talked some about that when you simplify that equation of the plane, that you end up with the coefficients of your x, y, and z terms in your equation of the plane correspond to those components of that vector. And they might not be the same as the components of the vector you started with, but you should end up with scalar multiples of the components of a vector you started with. So if I just pay attention, if I'm kind of fluent with that equation of the plane, and I'm clear about what all those numbers in that equation represent and how to work with that equation, then I recognize that when I have an equation of a plane given in this form, that those coefficients of my x, y, and z terms correspond to components of the vector that is perpendicular to that. So I have a 1 here, and a 2, and a -4. And I can use those for my vector that's going to be perpendicular to that plane and will be this vector along the line. So there's not really much work to do here, right? I'm not really doing a lot of math calculations. It's just a matter of recognizing what this equation is and what those values represent. All right, so this is a vector along the line. We've got a point on the line, a vector along the line, and we can use that to write parametric equations for a line. All right, so I'll just write that over here, similar to how that is given over there for line L. So remembering how to write parametric equations for a line, you're going to have x equals, y equals, and z equals. And this is the form for that, but remembering what numbers are what. So again, the constant terms here are a point along the line. So for this line that we're writing, those constant terms will be 1, 2, and 0. Of course, you don't have to write the 0 here, but and then the coefficients of t will come from the components of your vector. So remember that really what this represents geometrically, that t takes all the scalar multiples of this vector and translates them from this initial point that you started with here. Okay, so the coefficients of my t terms in this parametric equation of this line will be 1, 2, and -4. And of course, you don't have to write the 1 coefficient there or the 0 here. You can tidy that up a little bit. All right, so here's our answer to question 1, finding parametric equations for a line through point A and perpendicular to a plane. All right, and then the next question is determining whether two lines intersect or not. And when you think about lines in two-dimensional space, so just on a flat plane, basically there are three possibilities. the lines could be the same line. So this is from algebra. I think you might have thought about this when you solve systems of equations in algebra. You could have the same line, right? So the lines are right on top of each other. I'll use my markers here to illustrate some lines. So the same line. You could have lines that are parallel, so they don't intersect each other. Or you could have lines that intersect. Those are really the only three possibilities. So if they're not parallel, if they have some angle, you extend those lines out, they will have an intersection point somewhere. In three-dimensional space, there's another possibility. So you could have the possibility that they are the same line. So you could determine that. These two are not the same line. You could have two lines that are parallel. You could have two lines that intersect. But you also could have two lines that are not parallel, but also don't intersect. The easiest way to think about that is to think about the ceiling of the room you're in, if it's a flat ceiling, and think about a line going across the ceiling. And then think about the floor and a line going sideways across the floor, so forward and backward along the ceiling, across the floor. Those two lines are not parallel. They're not going in the same direction, but they also won't ever intersect. So you're thinking about two lines, like one on the ceiling and one on the floor. Those are not parallel and they don't intersect. Those are what are called skew lines. So really there's four possibilities here. They either are the same line, they do intersect at a point and we can find that, or they're parallel, or they are skew lines. Okay, so we're going to answer a slightly bigger question than what is actually written here. Not only do the two lines intersect, but if not, then how are they? All right, so a couple of things to pay attention to here. Notice that we have this vector here that we use to write the equation of this line, and then I have a similar vector that I can think about here. -1, 2, 3 would be a vector along this line. So if I think about that vector, that would be along line L, and I compare that with my vector here that's along the line we just wrote, you'll notice that those two vectors are not parallel to each other. They're not scalar multiples of each other. Because these two vectors are not scalar multiples of each other, these two lines cannot be the same line and they cannot be parallel. So we know that they're not the same line, and they are also not parallel, because if they were, these two vectors would have to be scalar multiples of each other. They would have to be going in the same direction or perhaps exactly opposite directions, but they might have different magnitudes. So not the same line and not parallel to each other. So that leaves two possibilities that these two lines could intersect. If they do intersect, it would be at a point, an XYZ point, or it could be that they are skew lines. All right, so when we talk about finding intersections of things, we're really looking at solving a system of equations. I have three equations here with x, y, z, and t, and three equations here with x, y, z, and t. So if we think about when these two lines possibly intersect, what that would mean is that their x, y, z points are the same points. What it does not mean is that the parameter value that would give that x, y, z point is necessarily the same as the parameter value in the other set of equations. So I'm really going to be looking at solving a system of equations here. My x, y, and z here would be the same as the x, y, and z here if those two lines intersect. That would be coordinates of a point. But the t that's here would not necessarily be the same as the t that's here. So you need to change one of these variables. Remember, t might be time, but in this context, really it's just a parameter. We often use t, but we could use some other letter if we want. So when I'm looking at tying these two equations together, though, I need to treat those differently. So I'm going to change one of them to a different letter. You could use subscripts to t1 and t2 if you want, but you need to distinguish between them. For me, it's easier to probably just change to a different letter. So I'm just going to change these to, we'll call them u here. Okay, but then we're just going to look at solving a system of equations here. So to answer question 2 here, we're looking at solving a system of equations. This set, and our x's should be equal. So 3 minus t equals 1 plus u, and the y should be equal. 4 plus 2t equals 2 plus 2u, and the z should be equal. -3 plus 3t equals 0 minus 4u. All right, so I want to solve this system of equations, determine if there is a t and a u value that make this true. If so, what are they? And if not, show that it's an inconsistent system. So there's a lot of ways to solve systems of equations. I'll probably just use substitution. I'm going to take this first equation and isolate the u. So I'll subtract 1 from both sides. So 2 minus t equals u. And then if I substitute that into the second equation in place of u, I will get, I'll go down here, 4 plus 2t equals 2 plus 2 times, substituting in for u, 2 minus t. 4 plus 2t equals 2 plus 4 minus 2t. All right, so if I add 2t to both sides of the equation, and subtract 4 from both sides of the equation, I get 4t equals 2, or t equals 1/2. I could plug that in and find a u value that corresponds to that. So 2 minus 1/2, so 3/2 will be my u value. All right, so I got the t and the u value from working with these first two equations. Those are just the two I chose to work with. But I have a third equation here that I haven't worked with. So I would need to check and make sure that this t and this u value satisfy that third equation. If not, then this is an inconsistent system. All right, so let's go ahead and check that. So in this third equation, negative 3 plus 3 times t, 1/2. And I want to see if that is equal to negative 4 times u. And it's not. Right? So here, negative 3 plus 3/2 is negative 3/2, and that is not equal to what we get over here. This is negative 12/2 or negative 6. Okay, so what that means is that this is an inconsistent system. If I had gotten that that was true, then those would be my t and u values that satisfy this system. I could use those t and u values to find an xyz point from either set of equations. But because this was false, this made this system inconsistent, what that tells us is that these two lines do not intersect. And we said there are really 4 possibilities. We already eliminated 2 of the possibilities. So the only 2 remaining possibilities was that they do intersect at a point. We just showed they do not, or that they are skew. So these 2 lines are skew. So like a line across the ceiling going one way and a line across the floor going a different direction, those 2 lines are not parallel. They don't intersect, and they're not the same line. They would be what we call skew lines. So they do not intersect, no. And in fact, the reason why they don't is that they are skew lines. Okay, we'll look at some more examples to do with lines, planes, and points in some other videos.